Right now, as you're listening this, you're part of the universe's biggest accounting error. According to the laws of physics, you shouldn't be here. I shouldn't be here. Nothing should be here. The universe should be completely empty, filled with nothing but photons bouncing around in perfect darkness. Yet here we are, and that's a problem, a big problem. See, when physicists started looking closely at how the universe began, they discovered something deeply disturbing. All our equations, all our beautiful theories about matter and energy and the fundamental forces, they all point to the same conclusion. There should be nothing. No stars, no planets, no you, no me, just empty space and leftover light. But clearly that's not what happened. Something went wrong in the universe's bookkeeping. And that error, that tiny glitch in the cosmic accounting system, is the only reason anything exists at all. Most people, when they think about the Big Bang, imagine some kind of explosion that threw matter outward into space. They picture chunks of stuff flying apart, cooling down, eventually forming stars and galaxies. That's not an answer. That's a label. The real question isn't how the matter spread out. The real question is, why is there any matter at all? Let me show you what I mean. In physics, we have this beautiful principle called symmetry. For every particle, there's an antiparticle. For every electron, there's an anti-electron called a positron. For every proton, there's an antiproton. They are identical in every way except for one thing. Their charges are opposite. And here's the kicker. When a particle meets its antiparticle, they annihilate completely. They turn into pure energy, usually in the form of light. Matter plus antimatter equals nothing but photons. Now, according to our best theories about the early universe, the Big Bang should have created equal amounts of matter and antimatter. Perfect symmetry. For every proton born in those first moments, there should have been an antiproton. For every electron, a positron. The universe should have been perfectly balanced. And if that had happened, if the universe had followed the rules we think it should follow, then within the first few seconds after the Big Bang, all the matter would have met, all the antimatter. They would have annihilated each other completely. The universe would have ended up as nothing but light, photons traveling through empty space forever. But that's not what we see when we look around. We see matter, lots of it. We see stars burning hydrogen, planets made of rock and metal, galaxies full of billions of suns. We see complex chemistry, biology, consciousness. We see a universe absolutely stuffed with matter. So where's all the antimatter? This is where most explanations cheat. They'll tell you that somehow more matter was created than antimatter. They'll use words like baryogenesis or CP violation, as if saying the word explains anything. You didn't explain it, you renamed it. Let me show you what we actually know, and more importantly, what we don't know. First, the observational facts. When we look out into space with our telescopes, we see matter everywhere. Hydrogen burning in stars, heavy elements forged in stellar cores, planets, gas clouds, galaxies. But we don't see significant amounts of antimatter. If there were equal amounts of matter and antimatter in the universe today, we'd expect to see a lot of annihilation radiation. Wherever the two types of matter met, we'd see characteristic gamma rays with specific energies, the signature of electron-positron annihilation or proton-antiproton annihilation. We don't see that. The universe is overwhelmingly made of matter, not antimatter. So somehow, in the early universe, there was an asymmetry. For every billion antiparticles created, there were about 1,000,000,001 particles. That tiny excess, that 0.0001% imbalance, is what we're made of. Everything you see, everything you touch, every atom in your body comes from that minuscule leftover. But why? Why wasn't the universe perfectly symmetric? Here's where it gets interesting. We know that nature doesn't always preserve symmetries perfectly. Sometimes symmetries get broken. And when physicists started looking closely at certain types of particle interactions, they found something called CP violation. C stands for charge conjugation, swapping particles for antiparticles. P stands for parity, flipping space like a mirror image. CP violation means that the laws of physics treat matter and antimatter slightly differently under certain circumstances. This was discovered in the 1960s by studying the decay of certain particles called kaons. James Cronin and Val Fitch found that when these particles decay, they don't behave exactly the same way as their antiparticle counterparts. The symmetry between matter and antimatter is slightly broken. Watch what happens when we stop guessing and start measuring. When physicists calculated how much CP violation we observe in particle accelerators and worked out how much matter-antimatter asymmetry this could generate in the early universe, they got an answer. It was wrong, off by about a factor of 10 billion. The amount of CP violation we can measure in laboratory experiments is nowhere near enough to explain why the universe is made of matter instead of nothing. So we have a mystery. We know there must have been some process in the early universe that violated the symmetry between matter and antimatter, but we don't know what it was. Here's where your intuition is about to betray you. You might think, well, maybe the Big Bang just happened to create more matter than antimatter by chance. But that's not how physics works. Random fluctuations in a perfectly symmetric system cancel out when you average over large scales. The universe is huge, much larger than the scale over which random quantum fluctuations could create a systematic bias. The asymmetry has to come from the fundamental laws of physics themselves. Somewhere in the machinery of the universe, there's a process that prefers matter over antimatter, and we haven't found it yet. This brings us to what physicists call the Sakharov conditions, named after Andrei Sakharov, who first figured out what would be needed to generate matter-antimatter asymmetry in the early universe. First, there must be some process that violates baryon number, the number that counts how many protons and neutrons you have. Without this, you can shuffle particles around, but you can't change the total amount of matter. Second, there must be C and CP violation, processes that treat particles and antiparticles differently. Third, these processes must happen out of thermal equilibrium. If the universe is in perfect equilibrium, forward and backward reactions balance out exactly, and no net asymmetry can develop. We've found evidence for all three conditions in particle physics experiments. But when we add up all the effects we know about, we still can't account for the observed matter-antimatter asymmetry. We're missing something big. This is the part your brain wants to reject. We exist because of an accounting error, and we don't know what caused it. At some point, you hit bedrock. And here's what we actually know: the standard model of particle physics, our best theory of the fundamental forces in particles, predicts that the universe should be empty. According to our most successful theory of matter and energy, there should be no matter and no energy, just empty space. But we're here. So either our theory is incomplete, or there's some piece of physics we haven't discovered yet. That's unsettling, isn't it? The entire material universe, everything from quarks to quasars, exists because our best theories are wrong about something fundamental. Now, we have some ideas about what might be missing. Maybe there are additional sources of CP violation in physics beyond the standard model. Maybe there are extra dimensions of space that we can't see directly. Maybe there are new types of particles that interact very weakly with ordinary matter, but played a crucial role in the early universe. Some theories propose that during cosmic inflation, the brief period of exponential expansion right after the Big Bang, quantum fluctuations could have generated the matter-antimatter asymmetry. Others suggest that the asymmetry came from the decay of very massive particles in the first moments after the Big Bang. But here's the honest truth. These are all educated guesses. We don't have direct experimental evidence for any of them. We're still missing the smoking gun, the mechanism that definitively explains why there's something instead of nothing. The universe doesn't care what feels satisfying. It doesn't care that we want a complete explanation. It just is what it is. And what it is, apparently, is the result of a process we don't understand. Think about the scale of this mystery. Every atom in your body, every atom in the Earth, every atom in every star and galaxy we can see, all of it exists because of a tiny violation of symmetry that happened in the first fraction of a second after the Big Bang. An asymmetry so small that it was only about 1 part in a billion. But that tiny difference is literally the difference between existence and nothingness. If that's true, then your common sense about why things exist is irrelevant. Common sense says that if something exists, there should be a reason for it. But physics suggests that maybe existence itself is fundamentally unreasonable. We're used to thinking of conservation laws as absolute. Energy is conserved, momentum is conserved, electric charge is conserved. These are the bedrock principles that make physics predictable. But baryon number, the quantity that measures the total amount of matter in the universe, apparently isn't conserved under certain extreme conditions. This violation of baryon number conservation is what allows matter to be created without an equal amount of antimatter. But the known sources of baryon number violation are incredibly weak. They would have negligible effects in the early universe. So somewhere there's a stronger source of baryon number violation that we haven't discovered yet. Or maybe our understanding of the early universe is fundamentally flawed in some other way. Let me give you a sense of just how mysterious this really is. Imagine you're an accountant and you're auditing the books of a company. On paper, everything should balance perfectly. Revenue minus expenses should equal profit. But when you add up all the numbers, you find that there's money left over that shouldn't exist according to the rules. That's exactly where we are with the universe. According to the standard model, our company handbook for how particles behave, the book should balance to zero. Matter minus antimatter should equal nothing but photons. But when we audit the universe's accounts, we find this huge surplus of matter that shouldn't be there. Now, as an accountant, you'd start looking for hidden transactions, unreported income, or errors in the bookkeeping system. Maybe there's a process you didn't account for. Maybe your understanding of the rules is incomplete. That's what physicists are doing right now. We're cosmic accountants trying to find the hidden transaction that created all the matter in the universe. And here's what makes it even more puzzling. We can see the evidence of this accounting error everywhere we look, but we can't find the mechanism that caused it. Take the cosmic microwave background, the leftover heat from the Big Bang that fills all of space. When we map this radiation with exquisite precision, we can see tiny fluctuations, little hot and cold spots that represent density variations in the early universe. These fluctuations are the seeds that grew into galaxies and stars and planets. But here's the thing. Those fluctuations are consistent with a universe that started with a very specific amount of matter. Not the amount we'd expect from perfect matter, antimatter symmetry, but exactly the amount we observe today. The universe has been carrying around evidence of this accounting error for 13.8 billion years. Wait, here's the weird part. We can measure the consequences of this mystery with incredible precision, but we can't explain the mystery itself. We know that for every photon in the cosmic microwave background, there are about 1.6 billion atoms of ordinary matter in the universe today. That's the precise accounting of our cosmic surplus. We can measure it, map it, trace its evolution through cosmic history, but we can't explain why that ratio exists in the first place. It's like being able to measure the exact amount of money in a bank account, track every deposit and withdrawal, predict future transactions, but having no idea where the original deposit came from. This precision is both impressive and humbling. We can describe the universe's matter content to extraordinary accuracy, but we're missing the fundamental explanation for why there's any matter content at all. This is where the detective story gets really interesting. Physicists are attacking this problem from multiple angles, and the scale of these investigations is staggering. Consider the proton decay experiments. If baryon number isn't perfectly conserved, then protons, the most stable particles we know, should occasionally decay. We've never seen this happen, but if it does, it would be smoking gun evidence for the kind of physics that could explain the matter-antimatter asymmetry. So scientists have built detectors deep underground, massive tanks filled with ultra-pure water, surrounded by thousands of light sensors. They're watching, waiting for a single proton in all that water to spontaneously disintegrate. These experiments have been running for decades, watching trillions upon trillions of protons, and so far nothing. That tells us something important. Whatever created the matter-antimatter asymmetry, it's not the simple kind of baryon number violation that would make protons decay quickly. The process has to be more subtle, more hidden. Then there are the particle accelerator experiments. At facilities like the Large Hadron Collider, physicists are recreating conditions similar to those in the early universe, colliding particles at enormous energies, looking for new physics that might explain the asymmetry. They're studying the decay of particles called B-mesons. looking for tiny differences in how matter and antimatter versions behave. They're measuring CP violation to higher and higher precision, mapping out exactly how and when the symmetry between particles and antiparticles gets broken. But here's the frustrating part. Every measurement confirms that the amount of CP violation we can observe directly is nowhere near enough to explain the observed matter-antimatter asymmetry. It's like finding evidence that someone broke into a bank vault, but the lock-picking tools you can find wouldn't be capable of opening that particular lock. There are also the cosmological observations. Satellites like Planck and WMAP have mapped the cosmic microwave background with incredible detail, measuring the temperature variations across the sky to a precision of microkelvin. These measurements tell us exactly how much ordinary matter existed in the early universe, and they confirm the accounting error. There's about 6 times more matter than antimatter annihilation can explain. But they also tell us something else. Whatever process created the matter-antimatter asymmetry, it had to happen very early, probably before the universe was even 1 second old. By the time nucleosynthesis began, when protons and neutrons started fusing into the first atomic nuclei, the asymmetry was already locked in. That's the weird part. It works anyway. All these different types of experiments and observations, using completely different methods and technologies, all point to the same conclusion. There was a matter and antimatter asymmetry in the early universe. We can measure its consequences with extraordinary precision, but we can't identify the cause. Here's the shift in thinking you need to make. Stop asking why does matter exist, and start asking how does matter exist. The why question assumes there should be a satisfying reason, some purpose or logic behind the existence of matter. But nature doesn't owe us satisfying reasons. Nature just follows rules, and sometimes the consequences of those rules are counterintuitive. The how question is more productive. How could the laws of physics generate a matter-antimatter asymmetry? What specific processes could violate the symmetries we thought were fundamental? How can we test these possibilities experimentally? This reframe changes everything. Instead of looking for some cosmic purpose behind our existence, we're looking for mechanisms. Instead of asking the universe to justify itself to us, we're trying to figure out how the machinery works. And that's actually more exciting than any philosophical answer could be. Because if we can figure out the mechanism, if we can understand exactly how the matter-antimatter asymmetry was generated, then we'll have learned something profound about the fundamental nature of reality. We'll know why the universe has the structure it has. We'll understand which symmetries of nature are absolute and which can be broken under extreme conditions. We might discover new particles, new forces, new principles that govern the behavior of matter and energy. Here are the key takeaways you should walk away with. First, your existence is not inevitable. According to our best current understanding of physics, the universe should be empty. The fact that it's not suggests that our understanding is incomplete. Second, symmetry breaking is real and important. The universe doesn't always follow the perfect symmetries that our equations suggest. Sometimes nature plays favorites. Third, the tiniest effects can have enormous consequences. A matter-antimatter asymmetry of just 1 part in a billion is the difference between a universe full of structure and complexity and a universe with nothing but light. Fourth, we're still learning. The biggest questions in physics: why there's something instead of nothing, what dark matter is, whether there are extra dimensions, remain open. The universe still has secrets. Fifth, mystery is not failure. The fact that we don't have all the answers doesn't mean physics is broken. It means physics is alive, still discovering, still pushing the boundaries of what we know. That's the weird part. It works anyway. Our incomplete theories, our partial understanding, our missing pieces, they still let us build particle accelerators, predict the behavior of stars, understand the evolution of the universe from milliseconds after the Big Bang to the present day. Physics works even when it's incomplete, but the biggest mystery remains. We are the universe becoming conscious of itself, asking questions about its own existence. And the deepest question, why is there something rather than nothing, remains unanswered. Maybe that's appropriate. Maybe consciousness had to evolve before the universe could ask questions about its own existence. Maybe we're not just observers of the cosmic accounting error. Maybe we're the mechanism by which the universe audits its own books. Think about this for a moment. You are a collection of atoms that exists because of an accounting error, and now those atoms have organized themselves into a pattern complex enough to contemplate the very error that created them. The universe made a mistake in its bookkeeping 13.8 billion years ago, and now part of that mistake has become conscious enough to discover that it shouldn't exist. That's not just scientifically fascinating, it's philosophically profound. We're not passive observers of some cosmic accident. We're active participants in the universe's attempt to understand itself. Every time we build a particle accelerator, every time we map the cosmic microwave background, every time we calculate the precise amount of matter-antimatter asymmetry, we're helping the universe figure out how it works. And here's something that should make you pause. If the accounting error had been just slightly different, if the matter-antimatter asymmetry had been smaller by a factor of 10 or larger by a factor of 2, we wouldn't be here to ask these questions. The universe would either be empty or would have collapsed back on itself too quickly for complex structures to form. We exist in a very narrow window of possibility, balanced on the edge of a cosmic accounting mistake that was calibrated to extraordinary precision. That's not evidence for design or purpose. It's evidence that the universe is far stranger and more delicate than our intuitions suggest. Reality doesn't care what feels reasonable, but it somehow managed to create beings capable of being unreasonable enough to question their own existence. And in doing so, it created the ultimate paradox: matter that shouldn't exist, organized into patterns sophisticated enough to realize that it shouldn't exist, using that realization to probe deeper into the mysteries of existence itself. The accounting error isn't just the reason we're here. It's the reason we're able to discover that we're here because of an accounting error. The mistake became self-aware, and now it's auditing the books that created it. The universe should be empty, but it's not. You shouldn't exist, but you do. And that's not a failure of physics. It's an invitation. Every time you look at your hand, remember, those atoms exist because the universe made an error, a tiny, inexplicable error that somehow led to chemistry, biology, consciousness, and everything you've ever experienced. We are all children of that error, products of the universe's biggest accounting mistake. And the most remarkable thing isn't that we exist despite the mistake. It's that we exist long enough and with sufficient complexity to discover the mistake and wonder about it. The next time someone tells you that science has all the answers, remind them of this. Our very existence is an unsolved problem. The fact that there's something instead of nothing is the ultimate mystery, and we're nowhere close to solving it. But that's not depressing. That's liberating. It means the universe still has secrets. It means there are still discoveries to be made, still fundamental principles to be uncovered, still ways that reality can surprise us. You are not an accident of chemistry. You are not a random collection of atoms. You are a temporary local organization of matter that exists because the universe's bookkeeping has an error in it. And now you're sophisticated enough to audit the books and ask, how did this happen? Understanding isn't comfort, it's power. The power to see that existence itself is the ultimate puzzle, and we're the part of the universe that gets to work on solving it. The accounting error that created everything is still being investigated, and you're part of the investigation team. Reality doesn't care what feels reasonable, but it gave us brains capable of being unreasonable enough to ask why anything exists at all. And that might be the most unreasonable thing of all.